All right, so with electrochemistry, we're going to be focused on um, reactions involving the movement of electrons. And with this, we're going to see that if one substance or one species, so it could be an element, it could be a compound, molecule, whatever it's going to be, but if one thing is losing electrons, something else has to be gaining it. So if we look at the reaction here, we can see zinc is going to the +2 state, so elemental to +2, whereas the hydrogen is going from +1 to 0. And we're going to see a balance there, just because we're going to have 2 of those hydrogens for every 1 zinc. And when we're trying to look at the movement of these electrons, what we can do is use the oxidation number or the oxidation state in order to kind of track how these electrons are moving from left to right. And then with this, not every reaction is going to have the electrons moving. So not every reaction is going to have the oxidation numbers change. So if we think about a double replacement reaction, for instance, 2 ionic compounds, we're essentially just swapping the positive and negative pieces, but we're not actually changing anything about the charges or the oxidation numbers there. So when we're looking at electrochemistry, though, we will see that something's going to have its oxidation number increase, something else is going to have its oxidation number decrease. And then with that reaction, when we're looking at the substance that's going to have the oxidation number increase, what we're going to be looking at is what's known as oxidizing, or the oxidation process itself. So in this case, if we look at it, zinc going from 0 to +2, so zinc is losing 2 electrons. That's why its oxidation number is going up. So in this case, zinc is being oxidized. And then with the hydrogen, then just the reverse is happening. In that case, it's gaining 2 electrons. And that's why we're seeing the oxidation number decrease. And like I mentioned before, with these reactions, we can't have one of these processes occurring without the other. If something's losing electrons, something else has to be gaining it. They can't just be disappearing into a vacuum, never be seen again, or they can't just be appearing out of nowhere. And then when we're looking at the other reaction, it's a little bit backwards, but the substance that's being reduced, so the substance that's actually gaining electrons, is going to be considered the oxidizing agent. And the way you can think about it in this case, if hydrogen is being reduced, we're going to consider that to be the oxidizing agent because it's essentially taking those electrons from zinc. So it's causing the oxidation of zinc to occur. And then just the opposite with the zinc, we're going to consider that the reducing agent because it's causing hydrogen to be reduced. So if something's oxidized, it's the reducing agent. If something's reduced, it's the oxidizing agent. And then with this, just to go back a second with the oxidation versus reduction, there's a couple different ways that you can kind of try to remember which process is going to be which. One of them is just going to be the term oil rig. And with it, we're going to be, again, talking about electrons. So with oil rig, oil is just going to be oxidation is loss. So we're thinking about electrons. If we're losing a negative, it's going to become more positive. So with oxidation, like we see here with the zinc, we're going to see that oxidation number increase. Whereas with the second half rig, reduction is the gain. And again, we're thinking about electrons. So if we're gaining a negative charge, we're going to have the oxidation number decrease there. And then there's also another one. So Leo says Gur. And with it, we're thinking about, I think it comes from astrology or whatever it is. But Leo the lion says Gur. So Leo losing electrons is oxidation. And then says Gur, the Gur part, gaining electrons is going to be a reduction. So again, in that case, we're seeing the oxidized species is going to increase in oxidation number. The reduced one will do the opposite. The reduced one's going to decrease. Then also, if we just think about it in terms of what reducing means in general, if something gets reduced, it becomes less, it gets decreased. We're seeing the same thing here. And then also just notice with it, the reduction piece doesn't necessarily have to become negative. So in this case, +1 to 0, we're seeing it decrease, but it doesn't actually become negative. It becomes more negative, it becomes less positive, but it never actually becomes negative in this case. And then with the oxidation in this one, it does actually become a positive number. But even if we had something go from -2 to -1, it's still becoming more positive, even though it's technically negative overall still. So with these oxidation numbers, when we're looking at oxidation and reduction, it's just a general comparison. So it's just, does it become more positive? Does it become more negative? But it doesn't necessarily mean it's going to become fully positive or fully negative. And then in order to actually determine if a um, reaction is going to be considered a redox reaction, so that's just the generally the term we use for oxidation and reduction is just redox. But in order to determine if a reaction is actually going to be redox, if we're going to have something become oxidized, if we're going to have something become reduced, we need to be able to look at that reaction, look at all of those different species, assign oxidation numbers, and then just compare the left and the right side of those reactions to see if anything increases, to see if anything decreases. So when we're doing that, we're going to have different rules we can use to assign these oxidation numbers. And the first one um, is just going to be if we've got a pure element, so just something in its elemental form, like we had with hydrogen and zinc in the last one. So zinc on the left is pure zinc, so it's got an oxidation number of 0. Whereas the hydrogen H2 diatomic element, excuse me, diatomic element, so it's going to have an oxidation number of 0. So even though we've got two of them, it's just that pure element. The overall charge is neutral, so we're going to see the oxidation number in that case is going to be 0. That'll be true for other diatomic species. But even if we've got multiple, as long as it's that pure element, the oxidation number is going to be 0. And then similarly, if we've got what's known as a monatomic ion, so if we've just got one element and it's got a charge, the oxidation number is just going to be equal to whatever that charge is. So if we go back here, we've got two of those in this case, even though we've got two of the hydrogens, we can still, when we're looking at the oxidation numbers, just focus on it individually. So the coefficient out in front is going to be important in terms of balancing the overall charge. That's why we can see a +2 overall on the left, +2 on the right, because we've got two of these hydrogens. But if we look at just the hydrogen itself on the left, it's just a monatomic ion because it's just hydrogen. It's just got that +1 charge. That's why the oxidation number for hydrogen on the left is just +1. And then similarly with the zinc on the right, just that ion by itself, so the oxidation number is just going to be equal to that charge. And then similarly, if we had just like a fluoride ion, -1, the oxidation number there would just be -1. Um, And then with these oxidation numbers, it's a little bit different than the actual charge, especially when we're looking at covalent substances. But we can kind of think of it in the same way. So when we're looking at a compound, we're going to see that the elements in that compound are going to have different oxidation numbers. And typically with the nonmetals, the ones that are going to gain electrons, we're going to see that those for the most part are going to be negative, and then the metals are going to give up electrons are going to be positive. So when we look at oxygen, group 16, oxygen's pretty much always going to have a -2 charge or a -2 oxidation number in a compound. The exceptions for that are going to be if we put it with fluorine. So since fluorine is going to be more electronegative, oxygen will have to actually adjust. So if we had something like oxygen difluoride, the oxygen in that case would actually be +2 because each of those fluorine are going to be -1. But for the most part, oxygen is going to be -2. And then another exception for that, in addition to the fluorine example, is going to be when we have it in a peroxide. So if you think about um, hydrogen peroxide, H2O2. So if we think about water, for instance, actually we can kind of see based on the second rule or second example at the bottom. The reason why oxygen is going to be -2 is because each of these hydrogens are going to be +2, +1, so giving us a +2 overall. And then we'll see with one of the rules coming up is the sum of these oxidation numbers has to equal whatever the charge is overall. So since this is a neutral compound, everything's got to balance out to 0. But if the hydrogens are each +1, that means the oxygen would have to be -2. But now with hydrogen peroxide, for instance, now we've got H2O2. So each of these hydrogens are still going to be +1. But now since we've got a second oxygen, each of those would just have to be -1. So with oxygen, there are a few exceptions, like hydrogen, or with the peroxides, for instance, as well as just with the fluorine. And then with hydrogen, as we saw here, pretty much always going to be +1. The exception is going to be if we put it with a metal. So if we had something like sodium hydride, NaH, in this case, sodium is going to give up an electron, be +1. Hydrogen is going to accept that electron, become -1. So because hydrogen only needs 2 electrons to fill its valence shell, it can go in either direction, can become +1 or -1. So depending on which type of element we have it with, that's going to determine what the overall oxidation number is going to be there. And like I said, fluorine being the most electronegative element, so fluorine is going to be able to overpower every other element. So if you've ever got fluorine in a compound, it's automatically going to be -1. If we had pure fluorine, so if we had diatomic fluorine, F2, then it would still be 0. But once we take fluorine and combine it with anything else, it's always going to have an oxidation number of -1, just because it's going to be the most electronegative, so it's going to be able to do whatever it wants. It's going to be able to just take that one electron it needs. That's why it's going to have the oxidation number of -1. And then that'll be, for the most part, true for the rest of the halogens as well. They're also going to be fairly electronegative, so they'll pretty much always be -1 in a compound. The exception, though, is going to be if we combine it with fluorine, then we'll have to kind of figure out what the halogen is. We'll kind of have to do a little bit of algebra to kind of see what that missing piece is. So if we think about, for example, chlorine and then 5 fluorines. Again, in this case, we're going to see that the sum of these oxidation numbers has to equal the overall charge. So since it's still a neutral compound, we're still going to have to have it equal 0. So what I like to do is just have the oxidation number for a single one of those elements first, and then above it, I put the sum of the oxidation numbers from all of those. So each fluorine individually is going to be -1, but since we've got 5 of them, it's going to equal -5. So when we look at the chlorine piece, we're going to need to have that balance. We're going to have to need it equal 0. And then in this case, since we've only got one chlorine, that entire chlorine is going to have to be +5. With it, it wouldn't work for this one, but just for an example, quick. If we had multiple chlorines here, so let's say we had 2 of them. Oops, let me use a different color so it's a little bit easier. Let's say we had multiple chlorines. We could put a 2 there, so this overall charge would still have to be +5. But then when we had 2 of them, we could divide it by 2 to get the oxidation number there. But it wouldn't work for this one just because then we'd have a fraction for the oxidation number. But again, with it, the halogens, unless we combine them with fluorine, we'll see that they'll be -1. Or if we put them with oxygen, which will also be more electronegative. And that's why we're looking at the oxyanions there. So that's going to be taking one of these halogens and combining it with some amount of oxygen. And then, as I mentioned, the sum of these oxidation numbers has to just balance out to whatever the overall charge is. So for a neutral compound, that's going to be 0. So we're going to need to have a balance between positive and negative between all of these different oxidation numbers. But with a polyatomic ion, now we're going to have something that's going to charge with it. So if we look at something like the carbonate ion, CO3, but now we've got a 2- charge. The way we can go through this and figure out what the oxidation numbers are going to be is just by setting up an algebraic equation. So for carbon, I'm just going to use X. And then for each of these oxygen, we've got 3 of them, but each are -2. And then in this case, we're not going to set it equal to 0. We're going to set it equal to -2. So if we take this, we're going to have -6. We can add 6 to both sides just to get X by itself. So let's see, in that case, X is going to be carbon. In this case, it's going to be +4. Whereas if it had been a neutral compound, we could still kind of go through the same process. It's just we would set that one equal to 0 there. So when we're looking to solve for the oxidation numbers, we just want to make sure we account for whatever that charge is. But both these rules are just saying essentially the sum of the oxidation numbers has to equal whatever the charge is. It's just in the neutral compound, the charge is just going to be 0 itself. All right, so if we look at a example like this one, we've got a nickel-cadmium battery, which is used in different types of devices. We've got the reaction, the redox reaction there that's actually going to generate that electricity. So that's just going to be the flow of electrons, electricity. In this case, we want to identify which substances are being oxidized and reduced, and then indicate which is the oxidizing agent and which is the reducing agent. So for this one, we need to actually go through and assign those different oxidation numbers. So if you want to kind of go through this one on your own first, see if you can kind of work through it without fully seeing how this is done. We're just going to go through and look at all of these individually and kind of go through, assign all of those oxidation numbers. So in some cases, we may have rules for one of those elements that we can use to solve for the other. In some cases, there's going to be kind of a couple different ways we could think about it in terms of identifying like the cadmium or the nickel. But take a moment to see if you can kind of use those rules we just went through and assign the oxidation numbers to all these different elements so we can see which is being oxidized, so which is increasing, and then the opposite, which is being reduced. All right, but just to start going through these ones, there's a couple that are going to be easier. So the cadmium is just that element by itself, it's going to be 0. And then with the water, we're going to see hydrogen will be +1, oxygen is going to be -2. And then with these ones, just note these are the oxidation numbers. So if we account for how many of these elements, that's where we're going to see the balance. Because note all of these are going to be neutral. So all of these have to have the oxidation numbers just balance out to 0. So in this case, 2 of these hydrogens are going to be +1, which balances out the -2 for the oxygen. So when you're assigning the oxidation numbers themselves, the coefficients out in front aren't going to be important. Those are going to be important when we start to look at what are known as half reactions and just sort of balancing everything. But in this case, when we're just assigning like the +1, -2, that's not going to change the actual oxidation numbers at all. And then if we look at the nickel oxide, we need to determine what the oxidation number is going to be. Each of these oxygens are still going to be -2. So that's going to give us a -4 overall. So we'll see the nickel there just has to be +4 then. And then when we go to the other side, there's a couple ways we could approach this. If we've got a polyatomic ion, we can kind of just treat that as one whole thing. So with both of these, we've got hydroxide, which is going to be -1, but we've got 2 of them. So that means the cadmium is going to have to be +2 to balance it. And then the same thing for nickel, actually. So when we look at the hydroxide, that's going to be -1 overall. So with the hydroxide, we could just try to solve for the oxygen and the hydrogen as part of this entire compound, or we could look at them as just part of OH minus. And either way, what we're going to see is the oxygen is going to be -2, and the hydrogen is going to be +1. And that'll be the same thing for the hydroxide on the other side. It'd be kind of weird if the polyatomic ion had different oxidation numbers, in different compounds, even though it's the same polyatomic ion there. So with the polyatomic ions, you can always kind of just remove those from the overall compound formula and just focus on that piece individually. But if you do that, make sure to include that charge. So when we remove the hydroxide, we had just OH minus. It's important that we had that minus there. Otherwise, we're going to wind up with completely wrong oxidation numbers. But with it, you can double check just to make sure you're on the right track. Because now if we look at it, we've got 2 of these hydroxides. So that's really going to give us a -4 from the oxygen, a +2 from the hydrogen. So that gives us a -2 overall there. balanced out by the positive 2 of the cadmium. And then the nickel 2 hydroxide is the exact same thing. So when we're looking at this, remember we've got those two different pieces. We need them to occur together. So if something's being oxidized, something's being reduced. And in this case, we're going to say the oxidized species is going to be the cadmium because it's going from 0 to positive 2. And then the nickel never actually becomes negative, but it goes from positive 4 to positive 2. So it decreases. So the nickel is going to be our reduced species. And then what we're going to see is that's going to make, I'm just going to put red agent, but that'll make the cadmium our reducing agent. And then when we look at the oxidizing agent, we're going to consider the nickel 2 oxide, nickel 4 oxide, excuse me, to be the oxidizing agent. So with these reducing and oxidizing agents, those are always going to be the reactant itself. So those are going to be the species that are actually causing this process to occur. And then with the cadmium, since that's just the element by itself, that's why we're just going to consider that to be the reducing agent, whereas the nickel is part of nickel 4 oxide. So we're going to consider that entire compound to be the oxidizing agent in this case. All right. And then with this, like I mentioned, if we have oxidation occurring, we also need reduction occurring. We can't just have those electrons just disappear or appear out of nowhere. We need both of those processes to occur. But when we're looking at these reactions, we can kind of actually separate those processes out, and we can write what are known as half reactions. And those half reactions are just going to be focused on either oxidation or reduction individually. And what we can actually do is use those half reactions to ultimately balance the overall equation for that chemical reaction. And when we're doing that, what we're going to doing is just assigning the oxidation number so we can see what's being oxidized, what's being reduced, and then we'll write a half reaction for each of those where we only focus on oxidation for the oxidation half reaction. We're only focusing on the reduction for the reduction half reaction. But in order to balance those, sometimes we're going to have kind of missing pieces there. So if we've got the we should be able to, I should say, balance everything but at least hydrogen and oxygen. So if we had like nickel in that half reaction, we should already have nickel on both sides. So we may need to add coefficients to one side or the other. But we should be able to balance all of those with the exception of hydrogen and oxygen. And then if we've got an excess of oxygen on one side, we're going to balance that by adding water to the other. And then just the reverse, or not just the reverse actually, but if we've got an excess of hydrogen on one side, we're going to balance it by adding the hydrogen ion, we're going to balance it by adding the proton to the other. And then just like with the mass, we need to conserve charge. So we need to have the same amount of overall charge on both sides of these equations. So if we've got an imbalance in charge, we're going to balance it out by adding electrons to whatever side is currently more positive. And then we'll do this for both of those half reactions. So we're going to have the oxidation and the reduction pieces. But with that, when we get to this point, it doesn't necessarily mean we're going to have the same number of electrons involved in each of those. So the next step is just going to be to take each of those half reactions, and we may need to only multiply one of them. We may not need to multiply either of them. We could have to multiply both of them, but we're just going to take those half reactions and then multiply them by some integer in order to make sure that the number of electrons involved in both of those. So one of them is going to be gaining them, reduction, one of them is going to be losing them, the oxidation. But to make sure that the number of those electrons is the same, we'll just multiply them by some coefficient. Because we can't have one half reaction that's gaining 6 electrons if the other half reaction is only giving up 3. So we're going to need the balance in terms of the electrons there. And then finally, if we want the overall balanced chemical equation, we'll be able to just essentially take each of those half reactions, add up everything on the left, add up everything on the right, and then just cancel out stuff that's on both sides. And then finally, you just want to double check your new equation, make sure that it is balanced, make sure in terms of mass it's balanced, make sure in terms of charge it's balanced as well. So if we look at the reaction here, we've got permanganate, MnO4, and then the oxalate ion, C2O4 with a -2. And what's going to occur here is we're going to essentially just wind up with the manganese ion, 2+, and then dissolves carbon dioxide. But if we look at this reaction, we can see it's not going to be balanced. So we've got an imbalance in the carbon, imbalance in the oxygen, and then with the charge as well, we've got -3 overall on the left, +2 on the right. So in order to go through this process, we're going to need to look at each of these elements, assigning the oxidation number, so then we can go through those steps we just did for the oxidation and reduction half reactions in order to determine what the overall chemical equation is going to be. And if we look at it quick, we can just assign those oxidation numbers here. So each of these oxygens is going to be -2. And we'll see that in the oxalate as well. Same thing in the carbon dioxide. So we can actually just put -2 everywhere. And then we'll see the carbon in that carbon dioxide, then it's going to have to be +4. The manganese, since it's just that ion, is going to be the charge itself, +2. So when we look at the manganese on the left, again, each of these oxygens -2, but it's -1 overall. So we can kind of do an algebraic equation. We got 4 of those oxygen, each is -2. It's got to balance out to -1. And then we can just use X to represent the manganese. So in this case, what we're going to see is the manganese on the left is going to be a +7. And then we could do something similar with the oxalate ion. It's just in this case, we would have it equal -2. And then we would actually have 2x, since we've got 2 of those carbons in this case. So we'll have 2x +4. And then again, multiplying it by the oxidation number of each of those oxygens. And then it's going to be equal to -2 because that's the overall charge. So we're going to see in this case, the carbon is going to be a +3. So if we look at the oxidation numbers, we can see carbon is going to increase +3 to +4. Manganese is going to decrease +7 to +2. And we can see an imbalance in those changes. So carbon's only going up by 1, manganese going down by 5, because we're going to need to change this reaction. We're going to need to add other pieces. We're going to need to balance it in order to get the half reactions to be balanced with one another to get the overall. And then also just notice oxygen is not changing at all. So oxygen is not being oxidized or reduced in this reaction. But yeah, just like I said, manganese is going to be getting reduced. Carbon is going to be getting oxidized. So if we wanted to look at the oxidizing and reducing agents, we would just consider the oxalate to be the reducing agent. Since carbon's getting oxidized, we would consider the permanganate, excuse me, to be the oxidizing agent since it's getting reduced there. But if we want to get the full balance equation, we're going to have to work through those steps we just saw with the half reactions. So for each of these, we're going to focus on oxalate going to carbon dioxide for the oxidation piece. We're going to focus on the permanganate going to manganese ion with the reduction half. So just looking at the oxidation one first, looking at the carbon. Again, we need to balance this. We've got 1 carbon on the right, 2 carbons on the left, but we've got double of that amount on or 1 and 2 on the right, double that on the left. So we can put a 2 in front of carbon dioxide. And now we have it balanced in terms of the mass. But with that reaction now, we've got a -2 on the left. We've got a positive or a neutral charge, excuse me, on the right. So we don't have that balance. We're going to need to add electrons. And now when we do that, we've got the balance of charge, we've got the balance of mass. So this is just going to be our oxidation half reaction. So when we look at the reduction piece, we're going to do the same thing. In this case, we notice one manganese on both sides, but we've got 4 of these oxygens. So when we've got the oxygen imbalance, we're going to add water to the other side. That's why we've got 4 H2O here now. But when we do that, now we've introduced hydrogen. So we're going to have to go back to the left and add in those hydrogen ions. So we're actually going to put 8 H plus here. And now if we look at it, we've got the mass balance. We've got 1 manganese on both sides. We've got 4 oxygens. We've got 8 hydrogens. But now we need to focus on the charge here. And we've got a positive 8 plus a negative 1. So we've really got a positive 7 here. We've got a positive 2 on the right. So we're going to need to add electron on the left in order to balance that out. In this case, we're going to add 5 of them, just because that'll give us a positive 2 on both sides of this reaction. And now that we've got both of those half reactions, kind of similar to Hess's law, where we're looking at multiple equations in order to represent one overall reaction, we can just take everything we have on the left, add it all up, same thing with everything on the right. But before we do that, we want to make sure that the number of electrons is equal, because in this case, the carbon is giving up 2 electrons total, but the manganese is gaining 5. So in this case, we're missing 3 electrons going into the reduction half reaction. So we need to think about what's going to be the lowest common factor in terms of the number of electrons here. And in this case, it's going to be 10. So we're essentially going to take this top reaction, just multiply everything in it by 5. So we'll wind up with 5, 10, and then 10 as the coefficients. Whereas the bottom one, we're just going to multiply everything by 2. So we'll wind up with 10, 16, 2, 2, and 8. And then when we do that, we can just take everything on the left, add it all up, take everything on the right, add it all up as well. And then the final step, similar to Hess's law, similar to spectator ions in some of those reactions, we can essentially look to see what do we have on both sides and just cancel it out. In this case, since we've got 10 electrons on both, we should always be able to cancel the electrons if you think about it, because we're going to have one of them on the products, one of them on the reactant side, and then we just multiply by those coefficients in order to make them equal. So we should never actually see the electrons themselves in the overall chemical equation. In some cases, we may also have like water or hydrogen ions or something on both sides. In that case, we would still cancel them, but if we don't have the same number, we'll still have some amount of those substances on one side of the reaction. But in this case, all we can do is cancel out the electrons. So we're going to see our final balanced reaction is just going to be the equation we have here. And then the one on the bottom, we can just see the overall reaction after we've removed those electrons from both sides. But we can check it just to make sure that it is balanced, because we've got now 16 hydrogens on both sides. We've got 2 manganese on both. We've got 8 oxygens with the permanganate, but we're getting 20 more from the oxalate. So we've actually got 28 oxygens here. So when we look at the oxygens on the other side, we're getting 20 from carbon dioxide plus 8 more from the oxygen. So we've got 28 of those, and then we've got 10 carbons on both. So with this, you can always make a table just to double check all of these different elements, but we also need to pay attention to the charge as well. And with the right-hand side, it's relatively easy because 2 of these are neutral, so just 0. And then we've just got 2 times a positive 2. So we've got a positive 4 charge overall on the right. When we look at the left, we've got to now account for all of these different species. So we're getting positive 16 minus 2 because we've got 2 of these permanganate. So now we're at positive 14. And then we're getting a negative 10 overall because each of these oxalate ions are going to be negative 2, but we've got 5 of them. So 14 minus 10, positive 4. That's what we see on both sides. So this is going to be our overall reaction because we've conserved mass. We've also conserved charge. So with this one, see if you can kind of do that same thing. So initially we'll want to assign oxidation numbers to all of these different elements, so we can identify what's being oxidized, what's being reduced. And then we'll kind of want to go through that same process where we may need to add oxygen to one side of the reaction. We're going to have to add electrons, of course, to both of these half reactions. We may need to add coefficients in order to get a balance. We can see difference in chlorines just quickly. But see if you can kind of do the same thing. And then with this one, since it says in an acidic solution, we don't really need to change anything about the process we just went through. So we could just add those hydrogen ions if we need to. We'll see with the next one, we'll look at a basic solution, and that's going to have one additional step because we'll essentially just have to add hydroxide in order to balance out any of the hydrogen ions we add. But for this one, if you want to pause it so you can have a little bit of a chance to work through it on your own, definitely feel free to do that. But I'm just going to start going through it quickly. And with two of these, the oxidation number is going to be very simple, just because it's going to be those monatomic ions. So the oxidation number is just going to be equal to whatever that charge is. And then with the other product here, it's just going to be diatomic chlorine. So it's going to be a negative, or it's going to be zero, excuse me, just because it's going to be that pure element essentially. So with the dichromate, Cr2O7, with a -2 charge, each of these oxygens are going to be -2. So if we think about it, that'll give us a -14 overall when we multiply it by the number of oxygen we have. So in this case, we've got 2 of these chromium, which I'm just going to use as X, minus 14 is equal to -2. So we can add 14. We're going to get positive 12 in that case. So we're going to see each of these chromium will just be plus 6. So when we're looking at this reaction, we can see the chlorine is going to get oxidized. It's going from -1 to 0. And then the chromium is going to get reduced, going from +6 to +3. So we can use that to just write our general half reactions. So chromate will be, or chromium, excuse me. Yeah, and this one actually, I have the entire thing here. But if we think about it, we'll have this as our first piece of the reduction half reaction. So in order to get a balance, we need to just put a 2 there. Gives us 2 chromium on both sides. But now we've got 7 oxygen on the left. So we need to add 7 water molecules on the right. But that gives us 14 hydrogens now. That's where we have the 14H plus coming from. So with this, you can kind of just look in the middle and kind of see how we're sort of bouncing back and forth. So first we had to add the coefficient 2 here. Then we had to account for the 7 oxygens by placing 7 water molecules on the right, which means now we've got 14 hydrogens. We've got to put those 14 protons on the left now. And then the final step is just to make sure that those are balanced. So since we've got a +6 overall on the right, we need a +6 on the left. Currently, we had +14 and -2. So we had a +12, but needed a +6. That's why we're going to have 6 negative electrons there. And then with the chlorine piece, it's a little bit simpler, because in that case, all we need to do is add a 2 on the left and then 2 electrons on the right in order to balance that charge. So we don't even need to worry about the water and the H plus at all in this case for the oxidation half reaction. But because we've got a difference in those electrons, we're just going to multiply this one by 3 in order to have both of them equal to 6. And then when we do that, that'll change this to 6, that'll change this to 3. So we can then just go through, look at these reactions, add everything up, and then the only thing in this case that's going to cancel will just be those electrons themselves. So that's why we still have H+. We didn't change anything about the coefficients for any of these. And again, chlorine minus is 6 now, just because we multiplied this entire thing by 3. Same thing for the diatomic chlorine. It now has a coefficient of 3, just because we tripled that half reaction in order to get the number of electrons balanced. But like I said, with this one, we're going to be able to also go through this if we've got a basic solution. Oops. The only difference is whenever we add those neutrons, or not neutrons, protons, excuse me, H+, since it's a basic solution, what we're going to do then is just add an equal amount of hydroxide to both sides of this reaction. So if we go back for a second, if this had been in a basic solution, we could still kind of go through the same process. But now that we've got 14H plus here, to both sides of this reaction, we would just add 14 hydroxide ions as well, because that would just then combine to give us 14 water molecules on the left. And then we would have just 14 hydroxide ions on the right, giving us those basic conditions. So with the basic solution, still follow those same steps. But just when we get to the balanced half reaction, look at the reaction. If we've got H plus there, we're just going to add an equal amount of hydroxide to both sides of that half reaction. So if you want to practice with this one, you can kind of do the same thing. Again, it's going to follow those same steps, but once you get the half reaction, we'll just add the hydroxide in. Whoops, that should be positive too. So with the cyanide, since nitrogen is going to be more electronegative, we can assign that oxidation number first, -3. With the permanganate, we just saw that one. +7, -2. And then now with this one, so those are going to be the oxidation numbers. If you want to try to pause the video, just give yourself a chance to work through actually writing out those half reactions yourself. Definitely feel free to do so. Okay. So with this one, we just saw that the carbon is going to be oxidized. The manganese will be getting reduced. So we can focus on those as our half reactions. With the carbon piece, the cyanide going to CNO minus. We've got a balance for the oxygen here. So we've got one on the right, we need one water molecule on the left, which means we need 2 of these hydrogen ions, which ultimately means we're going to need 2 electrons as well, just to have the charge balance, because we've got -1, -1. So we've also got a +2 here, we need another -2 just to balance out those charges. And then with the reduction piece, kind of the same idea. We've got 2 extra oxygen here because we've got 4 total, but only 2 on the right. So that's why we need 2 water molecules now, which means we need 4 of the hydrogen ions on the left to balance out those H's, which means we're going to need 3 electrons there as well. And then for this one, since it is going to be in a basic solution, we're then going to also just add in hydroxide ions. And we're going to add the same number as the H plus. So for the bottom one, we're going to add 4 hydroxide ions to both sides of this reaction, because we had 4 H plus on the left there. And then similarly with the top one, we'll add 2 hydroxide ions to both sides, just because we had 2 H plus on the right for that one. And then with the next step, what we're going to think about is the combination of acid and base, which is going to give us neutral water. So with the top one, we're going to combine 2H plus with 2 hydroxide on the right to just give us 2 water molecules. And then the same thing with the hydrogen and the hydroxide on the left. It's just in that case, we'll wind up with 4 of the water molecules there. So now if we look at it, these are going to be our half reactions. But we still need to make sure that those electrons are balanced. We've got 2 of them on the top, 3 of them on the bottom. So we're essentially just going to multiply those by the opposite coefficient to give us 6. So we'll multiply the top one by 3. We'll multiply the bottom one by 2 in order to just give us 6 electrons on both sides. So when we do that, oops, actually, in this case, you'll notice, if we think about it, 4 water on the left here. When we multiply by 2, we should have 8. But I only have 4 on the left there. It's just going to be because we've also got water on the right. So in this case, I'm just sort of accounting for what we have on both sides of these reactions for each of the half reactions individually. That's why with the top one, since we've got 1 water on the left, 2 on the right, we're just going to wind up with 3 overall on the right. So in this case, I'm accounting for the water that we have on both sides, basically. But I haven't accounted for the two reactions relative to one another yet. That's why we still have water in both of these equations. But now these are going to be our sort of our balanced half reactions. So what we can do is just, again, take both of these reactions, look to see what we have on the left, add it all up, look to see what we have on the right, and do the same thing. And in this case, you'll notice, if I can get the pen working, we cancel the electrons. We're not going to cancel anything about the permanganate, the manganese dioxide, cyanide, CNO minus. We only have all of those things in one spot. So we're just going to essentially be able to take both of these down to the left, both of these down to the right. But in this case, if you look, we've got 3 water on the top right, 4 water on the bottom left. So we're going to see the water are going to cancel, but since we had an excess on the bottom left, we'll still be left with 1 of those water molecules. And then similarly with the hydroxide, we've got 6 of them on the top left. We've got 8 of them on the top right. So we're still going to have 2 of them on the right there. So when we go to the actual balanced full equation there, what we're going to see is just going to be accounting for those substances that we have on both sides. And like I said, we're just going to wind up with 1 water on the left because we had 4 versus 3. And then we're going to have 2 hydroxides on the right because we had 8 versus 6 there. So we still were able to cancel some of them, but because we have an imbalance, we're still going to wind up with some of those substances on one side of our reaction. But if we look at everything else, 2 manganese, 3 carbons, 3 nitrogens, 2 hydrogens, and then with the oxygen, we've got 1 oxygen plus 8, giving us 9. We've got 2 plus 4, giving us 6, plus 3 more, giving us 9. So we've balanced the mass. And if we look at the charge, -1, but we've got 2 of them, gives us -2. Plus -3 gives us -5 overall. And then we see the same thing on the right because we've got -3 coming from all the CNO ions. We've got 2 more negatives coming from each of the hydroxides. So we've got a -5 on both sides. We've conserved the mass, we've conserved the charge. This is going to be our full balanced chemical equation then. And then with this, we'll start to see in the next piece how these redox reactions, how this oxidation reduction process can actually be used in what are known as voltaic cells, which are essentially just going to be batteries.